Hi friends, welcome to my channel VLSI Gyan. In this session, we'll see what is setup time for a flip-flop. Many times we come across setup time and hold time and setup time and hold time violations in VLSI. So let us see actually what is setup time. So let's get started. Before that, I request you to please like, share and subscribe to my channel. So friends, setup time is the amount of time that the input signal must remain stable. The input signal must remain stable before the clock edge of the flop to capture the data correctly. So this is the definition for the setup time. So it is the amount of time the input signal must remain stable before the clock. When designing the synchronous digital circuits, the input data needs to be stable and valid. It needs to be stable and valid for a certain duration before the clock edge arrives. So friends, this is the basic definition. So let us make it more clear by using a real-time example. Suppose friends, we are the passengers and we want to catch the train. And our train comes to our station and it halts for a very small duration of time. It is a very super fast express and it halts for a very small duration on our station. So what is expected? The thing is expected here is all the passengers who want to catch that train need to be arrived at the station and they need to be ready with their luggage and all in the platform before the train is arrived. They should be in a stable state. Then they can easily catch the train. So here also we are seeing the same thing, that the data which is present at the input of the signal should be stable before the clock edge or before the clock arrives. So before the clock arrives, your data must remain stable. It should not be changing. If it is changing, we don't know what is the value it is going to get settled. And that time an incorrect data may get cached by the flop. So the data must remain stable before the clock and it should remain stable for some duration of time. That some duration of time is called setup time. So setup time is the amount of time the data needs to be stable before the active edge of the clock. Similarly, in our real-time example, the passengers need to arrive the railway station before 5 minutes before the arrival of the train to catch the train properly, right? So the same thing, data needs to remain stable before the active edge of the clock so that the flop can catch the data, exact data, because data is settled now and you know what is its value, either 1 or 0, and the flop will catch it once the clock arrives. Data is ready. When the clock comes, the flop is going to take and it is going to capture that data. So this is what is setup time. So what happens if you do not follow this? Let us see much more in detail about this. So friends, so let us go to the another slide. Here you can see we have a launch flop and a capture flop. So these are the two flops which we have, and this is our data input and this is the clock. And this is some combinational delay between the two flops. So consider the situation in the capture flop. So this is the data input to the second flop and this is the clock. So what is expected is when you are getting the clock, before that only the data should arrive. So there is some time limit. Before that, the data should arrive and it should be in a stable state. It should be in a stable state before the arrival of the clock. It should remain stable for that particular duration before the arrival of the clock. So that what will happen? The capture flop will be able to catch the data properly. Otherwise, the capture flop will not catch the correct data. It may take some another data which is not the exact one which is required to be cached. So this is what is setup time. The flop should be able to catch the data properly. So for that, what is required? Before your clock is arriving your flip-flop, before the clock is arriving your flop, the data input must be stable, must come and it gets settled there. It should be stable for that particular window. That is setup time. So here also we can see in much more detail in the another figure. I'll show you. So basically, we all know that we have two things in VLSI which come all the time together. That is the setup time and the hold time. So friends, this C is nothing but the clock. So this is the clock which is coming, and you can see that it is at the positive edge of the clock. It is here, it is changing its value. So the clock is arriving at this point, right? So this is the window where your data should remain stable. So as we have seen that the setup time, TSU is nothing but the setup time. So the setup time for the flop. So the data changing, here it is allowed to change. But in this window, it is not allowed to change the data. Why? Because if it is changing here, there are the chances that the data may not settle to the correct value. And there are the chances, and definitely there is a possibility that the flip-flop may capture a improper data. So to avoid that, what is required? The data must remain stable. It should arrive before only, and it should get settled here before the arrival of the clock. So this amount of time, this is the duration before the arrival of the clock, the data must remain stable. So this is called the setup time. Similarly, we also require that the data should remain stable after the application of the clock. Means after the clock arrives, after that also a certain amount of time, the data must remain stable. After that, it can change. So here, this is called the hold time violation. Friends, I have prepared another video where I am explaining about the hold time for the flop. So please watch that video also. So in this video, we are concentrating only on the setup time. Right. So I hope that this concept is clear, that this is the amount of time, this is the minimum amount of time where the data must remain stable before the clock is arriving. Otherwise, it may lead to misconception that your data is not properly captured by the capturing flop. Next, we'll see another in detail, like what will happen if we are not following this, and what kind of the circuits are more prone to this type of the error. So let us see what are the circuits or the designs which are more prone to setup violations. So friends, we have seen what is setup time, and what are the circuits, or which type of the circuits or designs are more prone to setup violations. So the first number goes to the high speed designs. So high speed designs are the circuits which have a very high clock frequencies. So as the clock period is becomes very shorter, there is a less time available for the input data to stabilize before the clock edge. So these are the circuits, like we have USBs, serializers, deserializers, Ethernet, all this kind of the circuits where the clock is very high. We are using a very high frequency clock. So that kind of the circuits where the clock is very high are prone to setup violation. The reason is that the clock is high, the frequency is high. So we know that the frequency is inversely proportional to the time period. So time duration is very shorter for the data input to remain stable. So there is a chance of getting violated. Then we have the another kind of the circuits are asynchronous interfaces. Asynchronous interfaces are the circuits or designs, friends, where we are crossing multiple domains, multiple clock domains. Like we are not working on a single clock domain. We are moving from one clock domain to the another clock domain. The meaning is that we are not working on the same clock. There are the different clocks. So when you are moving from data from one clock domain to the another clock domain, there are the chances that there is a setup time violation. So the circuits like FIFO and UART, handshake protocols. Handshake protocols are like communication protocols which request for the permission before the actual transmission of the data. Three stages, like first is the transmission request, then the actual transmission, then the acknowledgement. Like this, handshake protocols are there. So that circuits or that protocols are also prone to setup violations. And also we have asynchronous FIFO. These are the circuits which are comes under the asynchronous interfaces, which are more prone to setup violations. And also we have the circuits like complex combinational logic. Complex combinational logic, like we have some arithmetic or some kind of the operation is going on, which is very complex. So that time the data may be taking the data path may be taking a longer time than expected, and the data may arrive late, and there is a chances of it's not becoming stable in that setup window, so that we can have setup violations. Next is data path with long combinational delay. If the combinational delay is very long, see friends, we have already seen in the previous diagram where I have shown two flip-flops in between a combinational logic. So if the logic is too long, then it may take more time and the clock may arrive faster and the data may come late. So there are the chances of setup violation. As suppose you are staying far away from the railway station and your train is arriving in time, and it took time for you because of traffic in the road, and you reach the station late. So what is the outcome? You are not going to catch the train. The same thing here. If the data path and with the combinational logic, a big combinational logic, you have a long combinational logic, it takes time to process and the data arrives late, clock is arriving faster. So there is a chance of not getting the setup time. The data is not stable during the setup window and it leads to setup violation. Then we have imbalanced clock distribution. See friends, we have different types of the clock distributions. So in that, the flops which are present in your design may not receive the day clock at the same time. So there may be the chances of skew, there may be the chances of jitter, and all this leads to again setup violation. Next comes the multi-cycle path. We have certain circuits which take more than one number of the clock cycle to process the data, and again they lead to delay in the data path, and your clock is arriving faster, your data is coming late. So again you have the chances of setup violation. Metastability issue. See friends, metastability is because of metastability, we get the setup violation, and also because of the setup violation, we get the metastable state. Metastable is nothing but it is a state where your data is not stable to a particular value. You are not going to get the expected output. Suppose you are expecting 0, you may get 1, or you may get some value which is not predicted. It is not in a stable state, undefined state. So you may get a you are not, suppose you are not what it is called, you are not knowing what the state it will go to settle, which is going to settle. So that time, if the whole design is affected by this metastability, so these type of the circuits are more prone to setup violations. Consequences of setup violations. So what happens if your setup window, the window means the amount of time during which your data must be stable, is not maintained. Your data is not stable. It is changing during that window also. So what will happen? So the first thing is it leads to functional errors. So suppose functional errors means for which you are designing the circuit. You are expecting that your circuit should function like this, but it is not functioning. So that kind of errors are called functional errors. Then you have timing errors. Timing errors, like your what time you are expecting and what you are getting, you are having different kinds of the violations, like setup violations, hold time violations, different kinds of the violation. So there is a timing failure in your design. Then metastability. It leads to your output going to an unpredictable state. So again, we have this consequences in setup time violation. Now, how to fix this? So friends, how to fix setup time violation? So the first thing we can do is clock tree optimization. So What is this clock tree optimization? It is like ensuring a well-balanced and efficient clock distribution network is very, very important to avoid setup time violation. So we need to check for the clock skew and latency and optimize it to minimize the timing disparities among the different clocks. Okay, next is pipelining. Pipelining is like to introduce pipeline stages in the crucial path. Like we have the critical path. So in the critical path, you can introduce pipelines to break them into smaller segments. So by reducing the overall delay, we have the chance of reducing the setup time violation. Then we can go for synchronization and gray coding. So in design with asynchronous input, like the input is asynchronous, or you have the cross domain crossing, like earlier we have discussed, like when your data is moving from one domain to the another domain, then you can implement synchronization techniques. We can implement synchronization techniques like two flip-flop synchronizers, mux based synchronizers, different synchronizers we can use to ensure that the data arrives in a synchronized manner. So for that, we can also go for the asynchronous FIFO because it uses gray code encoding techniques. And we can also go for gray code technique, which can be used to reduce the stability state. So the chances of going your output into a metastable state are reduced, and thereby you can reduce the setup time violation. The next comes is input delay insertion. Add delays to the input path of the flip-flop that are prone to the setup violations. So you can add delay to the input paths of the flop so that you can reduce the setup time violation. Next comes is the proper sizing and buffer insertion. See friends, like for every transistor, we have the transistor width and size are there. So the size also affects the performance of the transistor and the amount of the power it is taking and the size it is taking. And so all these parameters are very crucial. So we need to analyze the sizing of the transistor and gates in the critical path. Inserting buffers improves the signal integrity. We can insert buffers which increase the signal integrity. Then decreasing the logic delay at RTL stage. Friends, we can reduce the delay in the RTL stage by adding, by breaking down the logic into smaller parts. Thereby, the overall delay is reduced and we can avoid the setup violation. Next comes is timing constraints adjustment. See, friends, we have two methods here. One is timing constraints adjustment that we can do in the tool, which is always we are doing. So based on that, you can reduce the setup violation. And the other one is timing analysis and synthesis. Here we are using certain tools which are specifically used for reducing the timing errors. So like setup time and hold time violations. So for that, we are generally using some tools. So let us see what is timing constraints adjustment. So friends, timing constraints adjustment means we can increase the time for the data so that it can have some time to settle down. So that we can do in the timing constraints adjustment, and we can change the margin, setup margin. So likewise, we can adjust we can try to reduce the setup time violation. Next comes the timing analysis and simulation. Utilize timing analysis tools. For this, we can utilize and we can perform comprehensive simulations to identify and validate setup time violations. Like we have the different tools in Vivado. Also, we have certain tools which we can use. We have certain timing tools which perform the static timing analysis, and they try we using the tools we can fix the setup time violations. So friends, in this video, I have mainly explained what is setup time, what are the kinds of the circuits which are more prone to the setup time violations, and also how we can reduce the setup time violation. Hope you enjoyed the video. Please like, share, and subscribe to my channel, please, because it gives motivation for making more videos. And also, I request you to comment your queries in the comment section so that I can make more videos and I will try to clarify your doubts. Thanks for watching. Thank you.